If you've ever taken a course in statistics, there's a good chance that you've heard of the standard deviation. You probably have seen a formula that looks like this, or heard that it is a measurement of something called spread. But what does this really mean? In this video, we'll take a look at the standard deviation in a rather unconventional light. Let's say that you have a set of data and we want to consider how far away or how close the data points are in general to the mean. To begin, in a set of data, a deviation of a certain data point is how far away that data point is from the mean. The standard deviation uses these deviations to provide a measure of spread, which is defined as the measure of how far the numbers in a dataset are away from the mean or the median. But there's also a different measurement called the mean deviation, which takes the average of the absolute values of all the deviations in the set. And this gives us the spread because it is calculating on average the unsigned distance a data point is from the mean. However, for example, if we take these two data sets and calculate both the mean deviation and the standard deviation, we'll see that the mean deviations are the same, but the standard deviations are different, so there must be some difference between the two measurements. The usual reason given for this is that the standard deviation puts more weight onto larger values or outliers because of the square exponent in the calculation. But let's look at this from a different perspective. So first, we can replace the deviations with their absolute values, because squaring them will give the same result. We can now consider a dataset X having n points, and create two nth dimensional vectors, vector A having components corresponding to the absolute values of the deviations, and vector B having all components equal to 1. Given this, we can find the magnitudes of these two vectors, and we notice that they match the values in the standard deviation formula, so we can substitute them in. Next, we can consider the dot product of vectors A and B. Using the formula for the dot product, if we rearrange the terms, we can get an equation for the standard deviation. But the dot product of A and B is just the sum of the absolute values of the deviations, and the magnitude of b squared is just equal to n. In fact, we have shown that the standard deviation is the mean deviation divided by the cosine of the angle between A and B. First, if all the components of A are the same, then A is parallel to B, which means the angle between them is 0, so cosine of theta is 1. Putting this into the formula, this would mean that the standard deviation is equal to the mean deviation. But if we increase the angle between A and B, we decrease cosine of theta, so we'll increase the standard deviation. In this case, since A is going farther and farther away from B, the components of A will vary more and more from one another. This would mean that the deviations vary, which implies that there's more and more variance of the data points between one another. And this tells us that the standard deviation not only considers the distance from the mean, but how clustered the data points are from one another. To demonstrate this, if we look back at the two sets of data from before, and only consider distance from the mean, we can see that the mean deviations are equal. But in the first example, the data points are close to one another, while in the second they are more dispersed from one another, and accordingly the standard deviation is larger in the second example. And this matches with the original difference of the standard deviation from the mean deviation, because the more outliers there are, the less clustered the data points will be. It's important to note that since cosine of theta will equal 0 only if the dot product of A and B equals 0, and all components of A and B are either positive or 0, then the dot product will equal 0 only if all the deviations are equal to 0. In this case, every data point in the set would be equal to the mean. But other than this case, the equation will hold. And also, if the dot product is positive, then cosine of theta is positive, so we'll only be dealing with angles from 0 to 90 degrees.